Now we're going to look at space coordinates and vectors in space. First thing to understand are space coordinates, and they're very, very similar to the rectangular coordinates that we've looked at thus far. So quick reminder on that, that's just the regular XY plane that we talk about. Except now in space, we've got another dimension, right? We've also got the Z direction, right? X, Y, Z. And one way to represent that is like this. So I'm just going to draw it out over here. And it's a little hard to see, so you're going to have to, it might be a little new for you, but just you'll get used to it, I think. So X and Y are still here. Now we've just got another direction, right? So if, like, for example, if you look at me over here, you're looking on the plane of your screen, right? Your phone, computer, whatever it is. Now imagine like going from there to you, that's going to be perpendicular to the screen, and that's the other direction. It should be intuitive enough, hopefully, right? It's like the three directions around you. Okay, now what do we do with this? Well, remember how we used to define points in the XY plane? You'd first give your X coordinate, then you'd give your Y coordinate. Now, as you might guess, we just add a Z coordinate. So this point over here, what's this called? It's the origin. That would just be 0, 0, and then 0 for the Z coordinate. Oh wait, by the way, I think usually it's like X here, Y here, Z here. But since I drew it like this in the beginning, it's a little different, but the idea is the same, right? You can think about rotating. Okay, let's not do that. But point is there are different ways to draw it as well, and like depending on your textbook or depending on where you're learning it, it might be a little different. But like I think usually it's more like this. This is X over here, this is Y, and then up here this is Z. That's one way to draw it, and I think that's usually how it's done. But I drew it differently here. Doesn't really matter. The point is you first give your X coordinate, right? So not 0. This would be X, and then you give Y, and then you give Z, right? So it's not really, it's just basically an extension of the XY coordinates with an extra variable, extra dimension. Now, what do we do with this? How can we actually use this? Well, let's think about one uh, like area where one way in which we actually use the coordinates. So let's say we're trying to find the distance between 2 points, right? And I won't make it easy with the origin. I'll give you like some difficult points. First, I'll give it in 2D, try that yourself, and then we'll do it in 3D. So let's say we're starting at 1, 2, right? So this is 1, comma 2. I'm not going to label the axes because this pen is a little wonky. And let's say the other point is like 5 and 4 over here. What's the distance between these? Take a second, think about it, right? And you maybe connect it back to the last video we saw. You can make a vector over here and find the magnitude of the vector, exact same thing. And to do that, all we do is we find the components of this vector. So this over here, this would be 4, right? Is 5 minus 1. And this over here would be 4 minus 2, which is 2. So it's the square root of 4 squared plus 2 squared, right? If you want to save some time, you can take out 2 squared from here. So you get the square root of 2 squared. Sorry, it's so ugly, by the way. It's like nothing I can do about it though. And then this would be 2 root 5. Okay, sorry, it's really bad. 2 root 5. That's the magnitude. Easy enough. It's just it's basically the Pythagorean theorem. Now, when we're doing this in 3D, the only thing we're doing is adding the Z coordinate. Just like earlier when we added an extra comma spot for the Z coordinate, we'll do the same thing here. We just add another squared term over there. Right, so I'll draw it out properly this time, hopefully. So this is X. So this is X over here. This is Y. This is Z. Let's say our point is, and I'll give you 2 points, right? So like, let's say 1, so that would be like over here, 3 in the Y coordinate, in the Y direction, and then 4 over here. So, I mean, hopefully you could see me moving my mouse. Actually, I don't know if it's visible for you, but the point is like, it's hard to see, right? Because you can also think about this if you just like ignore the x-axis. You can think about that as a point like 2 comma 3 in the YZ plane. So it's a little difficult. So that's why, I mean, obviously we need the points to see. What did I say though? I said like 1, 3, 2. I think I don't even remember. Something like this. Let's say this is our first point. And actually let's give it a name as well, just for simplicity. Let's say that's P. Now we're going to take Q, and we're just going to make Q like 4, 1, negative 1. So that would be like here. Again, it's, maybe you can think about this as 5 comma 2. It's confusing, but anyway, what we said over here is 4, 1, negative 1. We want to find PQ, right? So PQ is just going to be the coordinates of Q minus the coordinates of P when we think about it as a vector. And I didn't mention this last time because I forgot. But to do this, you just take Q minus P. So Q minus P. And what would this be? Right? And it's like a vector, right? So that would be 4 minus 1. I'll write out everything, right? 4 minus 1. We have 1 minus 3. So because it's q minus v, don't mess up the thing. I mean, the magnitude will be the same whether this is positive or negative. But you still want to get the correct value, right? So negative 1 minus 2. So just make sure you do always stay consistent with the way you're doing it. The second one minus the first one. And this is of course 3, negative 2, and then negative 3. Now, how do we find the magnitude of this? Well, I think I mentioned this last time. I'm not fully sure. It's the same thing as the Pythagorean theorem. You're just adding another one. So it would be 3 squared plus the next component, negative 2 squared, plus next component, negative 3 whole squared. I should say whole squared, but I forgot. So now what is this? This is the magnitude of PQ. So what is the magnitude of PQ? Like, I mean, this part just try it on your own. It's straightforward enough. So only the square root of 9 plus another 9 plus 4. Maybe I did it wrong, but I think that's root 22. Yeah, 18 plus 4. So that's the answer. So if we think about it now, by the way, the vector would look, tell me which way, where would the arrow head go? Right? What's the initial point? What's the terminal point? If you said this, that's correct. Wait. Oops. Sorry. It should look like this because you're going from P to Q. Q is where you're ending. So that's the length of the vector. Good stuff. But it's still, we can make it harder. We can learn a few more things as well. Let's actually talk about spheres. Now, probably know what a circle is. Hopefully you do. And the equation of a circle as well is like x minus h squared. I'm not going to, it's very difficult to write with this. I don't know why. But yeah, it's like this, right? Actually, I'm going to give you a little chance, Take a guess. What do you think the equation would be for a sphere? I'll leave a little blank space here. This is r squared, right? So this is the equation that you have in 2D for a circle. And as you might guess, all we do is add this. Now, actually, I'm not sure what the letter is. It's H, K, maybe it's like J. But like J is also the directional vector for Y. So I'll just go with L. Just throw it in over there. This is what it looks like. This is the equation of a sphere. H, K, L, like H, comma, K, comma, L is the center of the sphere. R squared is the square of the radius. So R, or the square root of this, would be the radius, right? And exactly like a circle, you just go all the way around every point that's a distance of that away from the center. Over here it would be every point, and it's going to trace out like a sphere, right? So like this, then also like this and like this. So it's like a full. Do I have a sphere with me? No, but you know what a sphere is. I hope it's like a ball. So let's actually do a quick example now, and I'll make this fun. Um, I'll give you 2 points. I'll give you a diameter of the sphere, and then based on that, try to figure out the equation of the sphere. Right now, it might sound a little hard at first, but you know that it's a diameter. I'm not going to write it down because it's hard to write with this. But let's say these are the points: 1, 3, 6, 3, 1. Wait, actually, it should work, right? Yeah, I'm sure it's fine. And then 10, right? So we want to find the equation of the circle. Well, let's think about it. What are the x, y, z? I mean, those are just going to be in the equation. So all we need to find are h, k, l, and r squared. Now, when you think about a diameter, what's going to be in the middle of the diameter? The diameter passes through the center. It's equidistant on either side from the center. So the midpoint of the diameter is going to be the center. So what's the midpoint of this? Well, it's just p plus q over 2 because you're just averaging them out. And I'm not going to show all the calculations, but it's 1 plus 3 over 2, so that's 2. 3 plus 1 over 2, 2. 6 plus 10 over 2, 8. So this is the center. Just like that, like literally in seconds, we found h, k, and l. Now, h will be negative 2, k will be negative 2, l will be negative 8. Just be careful. Wait, no, sorry. H will be 2, k will be 2, l will be 8. So it'll be x minus 2, y minus 2, z minus 8. Sorry, I messed that up a little. Now, what about the radius? How do we find the radius? That's maybe a little trickier, but think about it, right? How do we define the radius? It's a distance from the center to any point on the circle. We know P and Q are on the sphere. P and Q are both on the sphere. So let's do that then. Let's just call this O, by the way, so it's a little easier, right? So what is the magnitude of OP? Well, let's think about it. It's going to be the magnitude of, we're doing P minus O. So 1 minus 2, that's negative 1. 3 minus 2 is 1. 6 minus 8, negative 2. And what is this going to be? It's going to be the square root of negative 1 squared is 1. plus negative 1 whole square is 1 plus 1 plus 4. So that's just root 6. Oh god, this is terrible. Root 6, root 6, root 6, root 6, root 6. So, very sorry about that. Luckily though, so okay, whatever, we know the stuff now, it's x minus 2 whole squared. Just finish it off from here. X minus, because it's extremely difficult to write with this. Y minus 2 squared, sorry to keep complaining, but it's like, and then k, sorry, z. Also, yeah, I mean, just write z how you want. I write it like this. In case it's a little confusing, like, I'll try to say it out as well, because some people think it looks like a 3 when I write it, but then when I write it like this, they think it's a 2. So, anyway, now what do we put over here? Just be a little careful, right? Remember from the equation it's r squared. So it'll be root 6 squared, which is 6. And just say that we're done. That's the equation. So fun stuff. Let's talk about component. There's a little bit more to discuss. I'll try to fit it in here. Let's see. So component form. Well, like I mentioned earlier, there's I, there's J, there's K, right? So now, if you're like 3, 4, 5, you'll be 3I plus 4J plus 5K, right? Normalizing a vector works the exact same way. You just divide by the magnitude. So if you wanted to find the unit vector in this direction, how do you do that? You just find the magnitude. The magnitude will be 5 root 2, I think. Some fun mental math there. Just divide it up like this, and that's it. This would be like v hat, right? Same notation. Something like that. And we're done. Now, what about parallel vectors? This is where it gets a little bit more fun. And parallel vectors are just, and a lot of like fun applications of this as well. Maybe not fun for you, but interesting nonetheless. So, wait. How did it work? Well, yeah, okay. Let's say you have PQ, right? This is going to have some direction. If you can write so PQ is a vector, right? Like the way with PQ, right? So let's just call this V. And then let's say PR is U. And I'll put the dots on U so you see. It's an umlaut, I think. PQ, PR. If we can write V as some scalar multiple of U, now they're parallel, right? So this would imply that V is parallel to U. And all that means is that the vectors face in the same direction. Wait, no, like like they're going in the same direction. And you can kind of like translate them around and get to the same thing. Now, how do we use this? Like, I mean, when would you actually, obviously if someone asks you, are the vectors parallel? Yeah, sure, use this. But like, what's another application? Well, notice how I started with P in both of these. That means the same point P lies in both of these vectors. Now, if they're parallel, think about it, right? You're starting at the same point and you're going in the same direction. Starting in the same point, going in the same direction. You're on the same line. So you can use this, right? If parallel, so if they're parallel, it means that it's the same line, right? Like I just showed you, right, with my hands. Not the most rigorous proof, but hopefully it gets a point across. Same line, which means P, Q, and R. What can you say about them? Well, I mean, yeah, same line. So they're collinear. That's one. That word gets used a lot over here. But that's one big idea, and I'm sure you can come up with other ones as well. Um, for example, now what if C were negative? Then you know that like Q is, so let's say P is over here. Q, this is hard. P is here, Q is here. Because R is negative, it's kind of in the opposite direction, so it'll be on the other side, right? So but I should just draw it here. So what am I doing? Let's say P is over here. This is PQ. Now, like assuming that C is a negative number, now maybe it's over here. It's still on the same line because the line extends infinitely in both directions, but they're on other sides of P. If it were positive, if R was like greater than 1, just like these aren't formulas that you need to memorize. You should just understand this. If R were like 10, it would be 10 times as far along as Q, and R would be here. If R were 1/10, it would be like here, right? Like small, like there, right? Hopefully that helps. It should make sense, but that's just one application. You can come up with other ways to use this stuff as well. But yeah, running out of time now. So main thing is it's just an extension of 2 dimensions, right? You're just adding the z coordinate, and basically every formula, all you do is adjust to include the z coordinate as well, right? It's just being inclusive, and that's never a bad thing. Magnitude works the same way. Finding the center, just the same logic as earlier. Same exact way to find the unit vector, find the directional the directional unit vector, normalizing a vector, all the same stuff. And then there's just this like extra bonus. It also works in 2 dimensions, but yeah, Hope this helps, and I'll see you in the next video.